So I spaced out last quarter and completely forgot to record the class last period. So I'm making sure to record this one. There's no section A to refer to. All right, so my goals today are to talk about makefiles, because I promised a quick refresh on makefiles, to talk about the ODP that's posted today, and then to go back to looking at linked lists and look at some of the pseudocode that we can use to start doing some of the things we need to do to linked lists, insert, search, print, and so on and so forth. So I'm going to start with the ODP, but any questions up front that don't fall into those categories, or that you want to ask first anyway?
Is the ODP as simple as searching for the valid ID?
Mm-hmm. That's all there is to it.
And how would you go about setting up a main program
to test it? I will tell you in a second. Let's take a look at the README, and then let's talk about main programs. So 203, you're basically writing your getNode function. Okay, so we're going to keep coming back to this picture of our linked list, which is an array of struct nodes. So there's 100 entries, and each entry is a struct node. And a struct node has three pieces. So there's data, which is an int. There's next, which is an int, and there's valid, which is an int. And so suppose we have a linked list that looks like this. So a list containing 3 nodes, 10, 20, and 30. And here's an example of what it might look like in our array. Assuming you've been adding things, removing things, making some changes, it's possible this is what our linked list might look like in memory. Maybe element 0 is our first node, and so that's valid. And maybe element 4 is our second node, so that's a 20 down at index 4, and that's valid. And maybe element 1 is our third node, so that's a 30, it's valid. And the next field for that would be null, since it's the end of the list. And then everything else in here would have a valid flag of 0. So how do we interpret this array of struct nodes, right? Start from index 0, 10 is our first node, and it points to another node which is stored down here at index 4. So that node has a value of 20, and it points to, I forgot to fill that in, points to the next node which is at index 1. So index 1 has a data of 30, and it points to null. There is no next node. And those 3 nodes have a valid set to 1, which means they're part of the list, and all the other nodes have 0. Okay, if we're going to create a new node to insert into this list, the first thing we need to do is figure out where in our array should we put it. We don't want to put it here because that's storing our 10. We don't want to put it here because it's storing our 30. We don't want to put it here, but we could put it right here, or here, or here, or here, and so on. So our algorithm is we're going to find the first entry in our linked list array where valid is 0. Okay, that's what your getNode function does for the ODP. Start at the first node in your array, check the valid flag. If it's a 0, just return 0. If it's not 0, check the next node. If that's 0, return the index 1. It's not 0, check the next node. Hey, I found a valid flag is 0, return the index 2. Okay, and now I know that element 2 in my array is available for use. And that's where your other code would create the new node. Edge case, every single valid flag is set to 1. There are no empty spaces in your array. In that case, getNode should return a -1. It's a flag saying we're out of space. So that's the essence of ODP 203, right? Search for the first node where valid is 0 and return that index. If there's no such node, return a -1. Does that make sense?
Yeah.
And this is almost exactly what getNode in PA1 should do, with one exception. In PA1, your getNode function, find the next free spot in the linked list array, set that node's valid field to 1, and return the node's index, or return myNull. So the only difference in PA1 is that in addition to returning the index 2, you should also set that valid field to a 1.
Will this work if you just add on the function to the same C program you compiled and sent last night? Would that still function? Because that way, if you did that for all of the ODPs, you'd have all the functions already in the file. You copy that and make that your PA1, have all the files ready.
Don't know for sure. For this one, it'll work, but in general, I'd say don't try that.
Do a separate file.
Yeah.
Change it.
Don't add extra functions in, because I may have a function inside main that's doing something,
Okay.
and that might interfere with it. All right, so this is basically another piece of PA1. This is the getNode function. So clear what it's supposed to do, right? And the code is as simple as you're probably thinking it is, right? Make a for loop from 0 to 99. If the valid field on that index is 0, just return that index. If you get all the way through your for loop and you didn't return, you know there's no open spots, return a -1. That's pretty much all you got to do.
I don't think I did that, but I think I got it all right.
Okay.
What if you don't use 99? What if you don't know that? What if it's an abstract number?
So this will not work unless we know what the length of the array is, right? Because we could just keep checking and eventually we'll find a 0, but is it a node or is it just, you know, part of the operating system? No way to tell. So C arrays, we got to know what the length is, and for this we're just assuming 100.
What about the null? What about checking the null? I mean the next.
We're not doing anything with next for this one, right? And next doesn't tell us whether the node is valid or not. Because, for example, if we delete this 20, the valid flag will get set to 0, but the next will still be 1. Unless we go through deliberately and clear the next flag, which we could, and then we wouldn't even need a valid flag. Except we'd have to know when we were at the end. So there's other ways we could do this. But the clean way is going to be check the valid flag. But there's things you could do to get the same behavior. All right, so let's say, go ahead.
Yeah, I just realized there's a slight flaw in my plan.
Okay.
In the program I implemented, I did while the valid flag is not 0, not equal to 0, which checks as the valid flag. It goes through a loop, and there's an if statement that checks the next node equals -1.
Oh, okay.
I just realized there may be a flaw.
Yeah, that may not be something you want to do. And my test bed may not catch that, but it might come up later on. All right, so let's say you want to test this. And this is something you're going to want to do throughout PA1, is build a data structure and use it to test some of your code. So how could we implement this inside a main program? Something like struct node linked list bracket 100. I'll use uppercase L's here so it doesn't look like pipes. Struct node LL bracket 100. And then it's just a bunch of assignment statements, right? You draw a picture. So use your init, right? Make a loop to set all of these valid flags to 0. And then make some assignment statements. LL bracket 0 dot data equals 10. LL bracket 0 dot next equals 4. LL 0 dot valid equals 1, and so on. And you just cobble together by hand this structure.
Is it necessary to set it to 0 before initializing it?
No, but I don't want to write 99 of these things.
Oh, yeah.
So I would make a loop first and set all the valid flags to 0, just so I don't have to do them all explicitly.
Didn't we initialize with the curly braces and a 0 inside?
Yeah, you can do it with curly braces too. when you declare it. It's a little trickier with structures, but yeah, it should be doable.
Is there any way to pass the length of the structure to the
Get node? You could define that it takes a second argument, which is the length of the array, and then you could pass it the array and the length. But for us, we're just going to hardwire everything to be 100. Because it's going to go away in PA2 completely, it won't be an issue.
So the out is just the name you prepare?
That's just the name I chose. Could be anything you want. All right, this is totally arbitrary. It's just the name of the array. So 3, 6, 9 assignment statements, and I've got this linked list stored in this array. And now I can call get node, and it should come back and give me a 2. And as I develop my other functions, like my print function, I should be able to call print, and it should print out 10, 20, 30. I should be able to call search 20, and it returns 1, search 25 returns 0, and so on. So it's going to be useful to be comfortable sort of building up these structures by hand. And that'll happen throughout.
So if it's an insert, so number 7, would you want it to go before 10?
Yes.
Okay.
And we're going to get to that. Because that's an edge case we need to deal with. All right, so let me touch on makefiles so I don't forget, and then we'll come back and we'll start looking at things like inserting and traversing lists. But let me do a quick run through on makefiles. So the general structure of a makefile, it's pairs of lines, right? And the first line is basically what we call a target. It's a thing that we want to build with a makefile, a colon, and a list of dependencies. A list of files that this target depends on. And then the second line begins with a tab and has what we call a recipe. Typically some Linux commands which are used to create this target. And this is just replicated as many times as needed. So let's actually make a makefile. So this is all garbage code. I just want a couple of things I can compile. I'm going to get warnings. Okay, I'll make it happy. All right, so we can build our main programming by saying gcc-o main main.c myfunc.c. The problem is that if we change myfunc and we want to rebuild our program, if we do this, we're recompiling myfunc. We're also recompiling main.c. And if you got a million files here and you change one file and you have a big long GCC, you're saying recompile all of those million files, and it takes a lot of time. So what we really like to do is partially compile main.c and partially compile myfunction.c, so we have these .o files, these object files, okay, which are almost fully compiled. They're ready to basically be linked together. And now to link them together, we just link the objects together. And this is a very fast operation compared to compiling. So now if I change my function, all I have to do is recompile myfunc.c, just this one line, and then link the objects together. Okay, so a makefile lets us create an algorithm, a prescription for how to build our executable program, taking into account all of these different kinds of dependencies. So let me show you a basic makefile. So target is main, it depends on these 2.0 files, and we use this GCC command to create it from those objects. All right, we need to know how to create main.o, so that's our next target, and it depends on main.c, and the recipe is just gcc-c main.c. And myfunc.o depends on myfunc.c. And there's how we build myfunc.o. So if all I have is my C programs and my make file, I can just say make, and it does the right things. It compiles main, it compiles myfunc, and then it links them together. Now if I update myfunction.c and I say make again, it recompiles myfunction.c and then it links everything together. If I haven't updated anything and I just say make, it'll say everything's up to date. Now let's say I do some includes in here. Let's say I include my own file, inc.h. And let's say both of these things depend on inc.h. Alright, so I make my file and it compiles everything and links them together. If I say make again, it tells me everything's up to date. Let's say I modify include.h. Now if I say make, it's going to recompile everything that depended on include.h, which was main.c and myfunc.c. But if only myfunc.c depends on include.h, I can remove that dependency from main.o. So my target's up to date. Now if I touch include.h and I say make, it's only going to recompile my function.c, because that's the only one I said depends on include.h. So it lets us do a more nuanced compilation and linking to build our target, but we have to create this make file that basically tells it what depends on what. But once you have this, anytime that you make a change and you want to build your executable program, you just say make. If there's nothing to do, it won't do anything. If there's a million things to do, it'll do a million things in the right order, and it'll give you an executable.
And you just go into VI and you just edit a file that says VI.
Just a file called makefile.
Makefile.
Yeah. And it just contains lines like this. And it's just a plain old file. Now, if you really, really, really hate the idea of makefiles and you really don't want to figure this out, here's the absolute lowball makefile. Two lines. Right? Technically this will work. And it'll work well enough when I'm grading your assignment that when I say make to build the executable, it will build the executable. But it's really no different from just having a script that says compile all my C code, give me an executable. Right? It's going to get you an executable, but it's not very efficient, and it's really not taking advantage of what makefiles are supposed to be able to do. So if you're in an interview and someone says, show me a makefile for building this executable, and you do this, you'll get the frowny face, probably. So it's worth thinking about this kind of thing. Yeah?
So to put it, to make it .o is to save like, what was?
So when we say gcc-c, it creates a .o. It basically changes the C into machine language. But it's not ready to run. Because, for example, if your program calls printf, nowhere in your program do you have the code for printf. You're just saying, I want to call a function named printf. But you haven't written the code for printf. Standard I/O doesn't have the code for printf, it just has a description of what printf looks like. So at some point there's something called linking. where the system will go through and it'll say, oh, okay, here's some code for printf. I'll put that into your program. Now your program can run. So it's putting different pieces together. That's what linking is, and that's going from a .o to an executable. But the actual compilation, changing C into assembly language into machine code, the ones and zeros, Engineering 270 assignment, that's what GCC-C does. And if you just say GCC-O, it does that, and then it does the linking. And if you want to have fun, use the -S switch. And that gives you the assembly language code that your C got converted to.
That's a lot of assembly.
It's a lot of assembly language for something that really doesn't do anything. And it's weird looking assembly language. All right, so that's a quick overview of makefiles. And you need a makefile for your programming assignments this quarter, so some version of it. And play around with this, right? Make yourself a directory with some files and just pretend that they do something. Don't start trying to understand makefiles after you've finished PA1 and you've got all your code working perfectly and now you start making a makefile. It's a really good way to corrupt your files. So don't do that. Practice in a different area, make yourself a new directory, and go crazy in there. Along those lines, let me mention something I mentioned last period also. Make sure you have some sort of backup methodology. If you were in 224, you've already heard this, so you're probably hopefully doing something, but if not, make sure you have some version of backup of your work from the server, from your own machine, and so on. Right? Hard disks fail, things happen. I don't run this server. This is provided by some service somewhere in the universe. They're pretty reliable, but it's possible at some point something happens and all the data that's on the Linux server goes away. Okay, and you don't want to lose your work. So make regular backups. The best way to do that is using something like Git. GitLab, GitHub. We've talked about this in 224. If you want to know about Git, come and ask me. But it's a way to push your stuff off into the cloud. Keeps track of changes. It lets you get back older versions of your code. You can pull your code down from anywhere to anywhere that you like. So you can make multiple copies, and it's completely free. So it's a really good way to do backups. Absolute worst case, get yourself a flash drive, pull your files down to your PC, dump them on a flash drive periodically. It's a good backup. When you're working in an area here, right, make a directory called My Backup and just copy all your files into there every now and then. So that if you accidentally do something like rm star, oh, I didn't mean to do that, right? I can go into My Backup and I've got copies of my files from whenever the last time was I did that, as opposed to starting from scratch. And don't be afraid to use tar. Right, tar cvf all.tar dot takes everything from this point on down and throws it into a tar file. And I can take that one file, I can transfer it to my laptop with WinSCP or SCP or whatever, dump it onto a flash drive, and inside that tar file is all of my files, the permissions, the date and timestamps, and so on and so forth. So there's lots of options for making backups. All right, so linked lists. I want to start by looking at some of the things we do with linked lists without worrying about the implementation. So I'm going to be sort of abstract here, but not completely. So here's a linked list. And we have a header, which somehow gets us to our first node. And let's say this is our linked list. So this corresponds to, right, this array structure in memory. And one of the first things you want to be able to do is what we call traversal. Traversing is just a fancy way of saying going through the whole list and typically printing out each node. But we'll talk about traversing trees and other structures as we develop them. So traverse is a general term for basically moving through your structure in some defined way and usually printing out the value of each node. So if we were to traverse this list, we should print out 10 followed by 20 followed by 30. Okay, how do we traverse a list? It's fairly straightforward. So our header somehow points to our first node. So I'm going to write some pseudocode. It'll look kind of like C, but it's not really C. It's something like C. So I'm going to make a temporary variable temp, and I'm going to set that equal to header. And I'm going to draw on my picture the word temp above this first node to let me know that temp is basically referring to this first node of the list. And I want to print out its data field, so I'm going to say print temp.data. All right, so we printed the first node's data value. Now we want to print the second node's data value. We have to find the second node. How do we find the second node in a linked list? We look at what the first node is pointing to. Right, this first node, temp, has a field called next, which tells us where the second node is. So it really takes nothing more than this. Temp equals temp.next. And as soon as we do that, temp is now referring to this node. And so now if we do a branch or a loop back up here to the print statement, all right, we printed a 10 already. Now we're going to say print temp.data. Well, temp is this node with a 20. When we print temp.data, it's going to print a 20. And now when we say temp equals temp.next, we're going to say, okay, temp.next points to this node, so temp has just changed to refer to this node. And we go back to the top of our loop. We print temp.data, which is now a 30, and we say temp equals temp.next. Well, temp.next is no longer pointing to a node. Temp.next is null, so now temp is equal to null. It's something like -1 maybe. Now, if we come back to the top of our loop and we say print temp.data, we've got a problem. Because we're trying to print the data field of what? Well, if temp is here, it's the data field of this node, but temp is null, there is no data field there, there's no node. So if we try to print the data field of that, we're probably going to get a seg fault, right? But we don't want to print anything here. Once we know that this temp node is equal to null, we know we've reached the end of the list. So this jump back up to the top of the loop should be conditional. We want to do this loop while temp is not equal to null. And that will code like a nice while statement in C. So at the very top we could say temp equals header while temp is not equal to null, print temp data, temp equals temp next. There's your whole loop. So that's a traverse routine, and it's a really good first routine to write. Because as you're writing the other pieces of your linked list package, for inserting, for deleting, and so on and so forth, if you have a function that you know will show you what's in the list, you can use that to help debug. So you can say, okay, I created this manually by doing a bunch of assignment statements. Call traverse, make sure it says 10, 20, 30. Okay, I'm going to insert a 15. So call your insert routine and then call traverse and see if it says 10, 15, 20, 30. If it says 15, 10, 20, 30, you know there's something wrong with insert, right? So this will really help you with debugging your other pieces. So traverse is a good thing to do first. And ultimately you need it for your print function for PA1. And again, this is pseudocode. Okay, this is not exactly what you're going to write in C, because in fact, when we say temp equals header, well, probably header equals 0. So we probably set temp equal to 0. And temp.data is actually linked list bracket temp dot data, right? Because linked list is the array containing our struct nodes. Temp is really an index in this array. So LL bracket temp dot data, that's what you want to print. And then to set temp equal to temp dot next, you're really doing temp equals LL bracket temp dot next. And you're doing this whole thing while LL bracket temp. Actually, you're just doing it while temp is not equal to null, or my null. But the thing is, this is not important, right? Well, it's important because this is what you're going to write to make your function work. But this is not important, right? This is a little more important. This is a little more important. This is what's really important. Okay, I want you to understand how to visualize these structures in a way that makes sense to you. So you want to get really good at drawing pictures, and then figuring out how you want to manipulate this picture to do certain things, and then writing code to perform those manipulations. That's what you're doing all this course. And the way you draw your pictures will probably be unique to you. Okay, they may not look like pictures that the other people you work with are drawing, or the pictures that I draw. You got to figure out what makes sense for you. This was the way that I ended up drawing linked list pictures for me, but it was slightly different from how some of my friends do their pictures. It's trying to it depends how visually oriented you are, and so on and so forth. So it takes some time. All right, so traversing, not too bad, right? It's a loop, and you can test your traverse code, make a structure in memory, implement some sort of linked list with a bunch of initializations, and then pass it to your traverse function and see if it works, debug it. All right, let's look at insertion. And insertion is going to take us into some interesting edge cases. So we want to insert, let's say, a 25. Here's the basic idea. We need to figure out the pair of nodes before and after where we want to insert our new node. Because ultimately our goal is to make a new node with a 25, have this prior node point to the 25, have the 25 point to the subsequent node. So to do the insert, the real challenge first is figure out which node is immediately before and which node is immediately after the node we want to insert. Now we're trying to keep things in order. So if we want to insert a 25, we can look at the first node, 10. We know it's got to come after that. So let's make a pair of variables, before and after. So we look at 25. Well, 10 is too small. 20 is also too small. It's actually got to come after this node somewhere, right? So this 20 should come before our node. So we're going to adjust these. We're going to move them forward one spot, set before to this, and set after to this. So we know 20 is before 25. When we look at 30, hey, that's after 25. We found the right spot to insert. Okay, so the first part of your insert is figuring out these two nodes that sandwich where the new node should go. And I'm just going to call this before and after. Once you've got this, it's fairly straightforward. So find before and after. then make a new node. So I'll call it temp. Set the data to whatever value you're inserting, 25 in this case. And then temp dot next should be what? Take a guess. More general though. After, right? Temp dot next equals after. Because we want this to point to the node that comes before, and before dot next should equal what? Temp. Perfect. And there's our insertion. 10 followed by 20, followed by 25, followed by 30. Okay, what we just did, that's what you want to spend your time trying to do. Right? So what did we do? We drew a picture, right? We created a new node and figured out how we were going to insert it. We were going to march through, find the two nodes that sandwich it, make some adjustments, and then write some code, pseudocode, C code, something to correspond to these changes we want to make. And then ultimately we got to translate this into, you know, compilable code like C. But it's this connection from here's what I'm trying to manipulate to here's how I do that in a program. That's the real gist of doing the programming assignments in here.
So are we just doing the brute force start at the beginning, go to the end? Where you want us to do like?
That's the only way to do it. Yeah, just start at the beginning and just keep marching through. So before, after, before, after, before, after. Keep going until the after node is bigger than the thing you're inserting. And then you're good to go. Okay, but this gets us into edge cases. So here's the edge case we're concerned with. What if we want to insert a 5? So we're going to make a new node with a 5. And we know that that should point to this 10. So we'll make a long wavy next pointer that'll come over here. But this before dot next equals temp, we want the prior node to point to the 5. Well, there is no prior node. 10 is the first node. Right? We don't have a before node. What we really need to do is somehow take this header and change that to point to this new node. And that's an edge case. Right? Header is in our case, it's probably just an integer that tells us where the first element in our list is, the index in the array. But if you insert something before that, where are we going to put that? So let's look at our memory map from our array of struct nodes. 10 points to 20 points to 30. And now I want to insert a 5. Well, I can put a 5 here. And I can mark it as valid. And I could say it should be followed by that node 10. But I've also got to somehow know that when I start to look through my list, I need to begin down here instead of here at element 0. There's an extra piece of information I need to modify somehow, and that's going to cause a lot of headaches. So we're going to completely avoid the problem. We're going to do a little cheat. Okay? And if you don't believe that this is going to save trouble, that's okay, but you want to do it anyway. And you can do it as just like, for some reason I'm supposed to do this, but it will save effort. So we're going to create what's called a Sentinel node. And a Sentinel node is one special node that always exists. We don't care what's in the data field. And its next field points to the actual first node of our linked list. So the Sentinel node always exists. It never moves. and it points to the first real node of the list. So our 10, 20, 30 list would look like this. And now if we want to insert a 5, we create a new node. And when we march through, we're going to initialize with before being our sentinel, after being the first node of the list. And the first time through that loop, we're going to say, hey, 10 comes after 5. We should sandwich in between before and after. And it's the exact same code we just wrote. We set the data value to 5. We set this thing's next field to after. And we set before's next field to temp. And there's no special case now. So for PA1, PA2, we're going to use Sentinel nodes, right? And it's just this fixed node that never moves around. It's always present. And all it's there for is to point to the first real node. So if we have an empty list, this is what it looks like. It's a Sentinel node that's pointing to null. And we'll understand this is an empty list. So when we do something like traverse, we need to be careful. We don't want to start off with temp equals header. We want to start off with temp equals header.next. So that temp the first time through is actually the node after the Sentinel. Or if the list is empty, it'll be null, and we'll kick out of our loop right away. And that saves us another edge case. So in PA1, your init function, which you already wrote hopefully, says index 0 should point to my null. What you're doing there is you're creating a Sentinel node at element 0 in your linked list array and setting the next value to indicate an empty list. So that points to my null, indicating there are no other nodes in the list besides the Sentinel. So this picture wasn't including a Sentinel node because, in fact, this is where your Sentinel is going to be. And we wouldn't actually store the 10 in that first node. It would simply point to where we store the 10. It's up to you what you do with the valid flag in the Sentinel. Since we know the Sentinel is always there, you can completely ignore this, or you can set it to a 1 and maybe simplify some stuff.
So will our PA assignment eventually include all 100 things, including the Sentinel node? So there's 99 elements?
So PA1, we can have 99 actual things in the list because element 0 is always a Sentinel. So the most you could insert is 99 numbers, and then it would be full.
So should we track for an education in which the user asks for 0?
Asks for 0, what do you mean?
Tries to insert into 0?
0 is fine. Oh, so the user will not ask to insert into a particular location, right? They'll say insert this integer, and it'll look at the numbers in the list and figure out where to put it to keep the list in order. But the main program, the user should never actually deal with this thing as an array, right? That's only your functions that are going to deal with that. And that's part of, again, of this idea of an abstract data type. Because in PA2, we're going to throw this out the window, and we're going to have a totally different implementation. We're still going to have a Sentinel node. We're going to have those same 5 functions, but it's going to be implemented totally differently. All right, so where does this all leave us for the end of Thursday? Get really good at drawing pictures, right? Get a nice soft pencil and a good eraser and thick paper or a whiteboard or a chalkboard or something, because you're going to be drawing pictures for the next 25 weeks. And 2 quarters and some space in between. Yeah, probably like 23 weeks. And start thinking in terms of first go-to should be, what do I want to do to this picture, right? Trying to understand an algorithm with code is frustrating for most people. What you want to try to understand is, how am I trying to manipulate this structure? And we're going to draw pictures, and it's like, okay, I want to delete the 20. Well, I need to find the node that comes before it and have that point where the 20 was pointing. I want to do this. And then you take what you just said to yourself and you start trying to write some pseudocode to do that. Well, I need to find the node that I'm trying to delete, but I need to remember the node that comes before it. So I want a pair of temporary variables, something like a before and a current. And when I find that current is the node I want to delete, I set before.next equal to current.next. And that's a few lines of pseudocode. And then test your edge cases. Will that work if I delete the last node? Will it work if I delete the first node? Will it work if I delete something in the middle? Yeah?
I don't think we discussed how to test our ODPs.
The
Or how to build a main function that we use to test it.
Yeah, so your main function, make your struct node array, do some assignments, and we don't care about the data next, so just go through and set all of your valids equal to 1, and then, I don't know, set element 3 to have a valid equal to 0, and then pass that to your get node, make sure it returns a 3. And then put that back to a 1, maybe change element 17 to be a 0, and call your get node, make sure it returns 17. And then put that back to a 1, so everything's a 1, call get node, make sure it returns a -1.
So we could just pass the structure into our get node
Mm-hmm.
and hopefully get what we're looking for.
Yeah, so you're passing a pointer to a structure, you're passing an array of these struct nodes. I already closed the README, but it's prototyped with struct node star LL, right, which means LL is an array of struct nodes. So pass that in and see if it finds the first node that's set to a 0. Cool. All right. So play around with that. Tomorrow I want to start looking in more detail at insertion, deletion, and searching using this before-after business with a Sentinel node in the mix. We'll put together some pseudocode for all of that, and we'll see that most of the edge cases have gone away. Most of the things where you're working at the end of the list work exactly the same as in the middle of the list. So we'll do that, and at the end of tomorrow, you should have a pretty complete idea how to do pseudocode for all the pieces of PA1, and then you're off and running.